In this demonstration, we're going to show how to model a ratchet mechanism with a lead screw. Our system consists of a screw connected to a ratchet. We're going to drive the ratchet with an oscillating input torque, and the ratchet will only permit the screw to rotate in one direction. On the screw is a lead screw. It will translate as the screw rotates, and the lead screw is acting against a mechanical load. We're going to model this system using SimDriveLine. When we're finished, the model will look like this, and we'll see during simulation that the screw only rotates in one direction and that the lead screw cannot be back-driven by the mechanical load. I'll now switch over to the Simulink environment so you can see how this is done. SimDriveLine can be found beneath Simscape in the Simulink library browser. We'll open up a new Simulink model and build our mechanism here. The first thing that we'll need is a model of the ratchet. We'll model the ratchet using a unidirectional clutch. We're going to drive the ratchet by specifying the input speed. So we'll use an ideal angular velocity source to actuate the clutch. This actuation has to be relative to another point. So we're going to actuate it with respect to another fixed point in space, which we'll define using the mechanical rotational reference block. So this allows us to specify the input speed at which the ratchet will be driven. We want the ratchet to oscillate so that the lead screw will move. That oscillation we'll define using a Simulink signal from this sine wave block. We'll need to specify the units for the speed at which we'll drive the ratchet. To specify the units, we'll use this converter block. The converter block allows us to specify the units of the signal. We'll connect that here and specify the units to be radians per second. The next component we'll need is to model the inertia of the screw. So we'll use an inertia block to do that. We'll connect that here, and this is where we'll specify the inertia of the screw. The next component in our mechanism is the lead screw. We'll go down to Gears, Rotational Translational, and bring in the lead screw model. If we double-click on the lead screw, we can see what we can specify. We can add friction losses, so we'll specify constant efficiency. We could also have left it as an ideal lead screw. We can also specify viscous losses, and we'll set those to 250. The next thing we'll need to do is to specify the mass of the lead screw. We'll do that using this block. We'll bring this mass block into our diagram and connect it to the lead screw. The lead screw is going to act against a spring or a mechanical load. So as the lead screw moves, the spring will act to push against the lead screw, driving it in the other direction. The spring needs to act against something, so we'll have it act against a fixed point in space using this mechanical translational reference block. The mechanism has now been modeled. What we'll need to do is to use sensors and scopes so that we can view the results of the simulation during the simulation. So we'll use an ideal rotational motion sensor block in order to sense the rotation of the screw so we can see how fast it is rotating. This measurement needs to be with respect to something, so we'll have it measured with respect to a fixed point in space. We'll also want to measure the displacement of the lead screw, so we'll use a translational motion sensor, connect it to the lead screw itself, and measure with respect to a fixed point in space. We'll want to view the results during the simulation, and we'll view them on the results on a Simulink scope. We'll want to specify the units of the signal we're viewing on the scope, and we'll do that using these converter blocks. So we'll connect this to the position of the lead screw, and we'll copy and paste to measure the speed of the lead screw, the rotational speed of the screw itself. The last step is to specify the solver that we'll use. Because we're modeling a physical system, there is additional solver technology that we'll be using, and we will need access to different solver parameters. So we will use the solver configuration block to have access to those. And finally, we'll select the global solver for the simulation. Since it is a physical system, we'll use a full implicit solver. At this point, we can run the simulation. So we're going to set the simulation time to 50 seconds. We're going to open the two scopes and run the simulation. We can see that this is the velocity of the screw, and it only rotates in one direction. So our ratchet is doing what it is supposed to do. And when we look at the displacement of the lead screw, we can see that it only displaces when the ratchet is driving it. The the spring or the mechanical load that it is acting against is not capable of backdriving the lead screw. In this demonstration, we have seen how we can use SimDriveLine to model a lead screw and a ratchet mechanism.